All right, next part. Let's try another example. Here, nitrogen 14. And in this example, there is an alpha particle that hits it, right? It hits it, it creates a nuclear reaction and changes it into oxygen, and one proton is knocked off, right? We have the masses of the nitrogen nucleus, we have the masses of the oxygen nucleus, correct? So you get again reactants minus the products, right? We already know the masses of the alpha particle and the proton, so I did not include that there. And you get, well, it's a negative now, right? And you have to think about this. The positive meant the released energy, right? So in this case, there's a negative energy, and this negative energy means that it needs energy for this to occur. And it will need it in the form of the kinetic energy of the alpha particle, right? So kinetic energy will be absorbed and used, and it will be, well, this mass difference times 931.5. So you need 1.2 mega electron volts to make this reaction occur, right? So it will not occur by itself, right? Because it needs energy. If you don't give it this energy, this will never occur. This is not a natural process. Right. Moving on to the next part, fission, which is something we are very interested in, right? Nuclear reactions. This is the reactions that power nuclear power plants, fission, right? Fission, basically you get a uranium-235 atom, and you make it absorb a neutron, right? So there has to be neutron. It is absorbed by this uranium atom, and it turns into 236. 236 is unstable. It will break apart. Right? So, what we want to do now is we will take the energy of the reactants as just uranium-236, which is given here. This is the mass of the uranium nucleus. Very careful again. This question was designed with only the nuclear masses in mind, right? If you ever have the mass of the atom, you have to subtract the mass of the electrons first. Right? Next is these three are the products, right? Here. Barium has this atomic mass. Krypton, that. 3 neutrons. Neutrons times 3. And you subtract. And there's a mass difference that is positive, so this means that energy was released, right? Energy having been released, there's 173 mega electron volts of kinetic energy released. Quite a lot of energy, right? So this is one way to do this. If you did the same process using binding energies instead, you would get the same result, right? Because mass difference is the same as the binding energies. Using the same process with binding energies gives you the same result of 173 mega electron volts. So in this case, because if you don't know the masses and you do know the binding energies, you can use this. A way that a question might be given to you is that you might giving again this graph, right? Using this graph, you're able to get the binding energy per nucleon. You can convert it to the binding energy of the whole atom, whole nucleus, and use that binding energy to calculate this result. Okay? Let's go back down. At this point, is there any questions related to this concept of nuclear fission? So there's several observations we should make when looking at this. Right? The first observation has to be that this reaction requires a neutron, right? And it releases 3 neutrons. So if you do it once, you start it, right? You can just give it 1 neutron and you'll create 3. So these 3 neutrons can keep the reaction going, right? And if it keeps going, the next reaction will also release 3 neutrons, so it can keep going again, keep going again. This is what we call a chain reaction. So we go down, and this we will call a chain reaction. Chain reaction. Basically, this means that one of these reactions will be able to create more reactions after it in a series. You have to know that. Second thing, you should know this is an induced process. Which means if you do not give it the first neutron, it will never start. Correct? The last vocabulary word you need to know here is something called critical mass. And what is critical mass? Well, if you have a sample of this uranium, right, it has a certain number of atoms. If you shoot it with one neutron, it will start one reaction, right, if it's absorbed, and it will release 3 neutrons, right? To keep the reaction going, at least one of these neutrons has to be absorbed, right? Because it's not guaranteed, right? These neutrons can just escape as well. If they escape, you do not continue this reaction. And there's a probability of it being absorbed. If you have more uranium around it, it means there's more chance that this will be absorbed, and this means that the reaction can continue. So the probability of it being absorbed is depending on the mass, right? And there's a certain amount of mass where the probability is 1/3, right? And we call this the critical mass. If the probability of one of these neutrons being absorbed is exactly 1/3, it means that every reaction, at least 1 neutron is absorbed, and it keeps going forever. If it's less than 1/3, then the number of neutrons in reactions keeps going down, right? It keeps getting reduced, and then at some point, it's gonna stop. So critical mass is the mass required to keep the reactions going at a constant rate. There's another side to this. If you get a higher mass than this, the probability is higher than 1/3, and the number of reactions keeps increasing, and keeps increasing. And eventually, right, it goes there is no limit to this. It's an exponential increase. So it peaks until the point where everything reacts at the same time, and you have a nuclear explosion. Or a meltdown, whatever happens first, right?